Right. For this session, let's talk about the part two of the introduction to earthquake hazards. And let's start with the slope movement or the slopes, your landslides, and your embankments. First, there are two main types of earthquake induced slope movement. So you have your rock slopes, which include, of course, your natural rock. And you also have your soil slopes, which can also include natural and engineered slopes like embankments, cut slopes, and so on. Right, for rock slopes, you have two main types of movement. You have your fall or your free falling materials that are detached from a steep face like a cliff, a cave, an arch, or a tunnel. For slides, these involve shearing displacement along a defined or distinct failure surface. Now, for soil slopes, the failures can include falls, slides, flow slide, and lateral spreading, as discussed previously. And note that different types of slope movement can initiate in a wide variety of slope angles. Right? So at this point, I would like to point out or emphasize that slope movement hazards or slope failure hazards are poorly represented by slope angles. For example, rock falls initiate at an inclination of 40 degrees or higher. Okay, so any slope that is 40 degrees to 90 degrees are prone to rock falls, soil falls, and other falls. While you can get lateral spreading at inclinations as low as zero point 0.3 degrees, right? So that's fucking gentle, right? Zero point 0.3 degrees is flat. It's very, very flat. And at those slopes, lateral spreading can still initiate. Okay, so when you are talking about seismic slope instabilities, almost all slope angles are covered or are susceptible to to different types of earthquake induced slope movement or slope failure, right? So this is a table showing different types of rock slope failures or rock slope movements, right? So we have your rock falls, rock slides, rock avalanches, and rock slumps, and rock block slides. So first, rock falls are all about, of course, detached blocks that are falling or rolling or bouncing, and they start at slope at inclinations of 40 degrees. For rock slides, are these are uh, blocks of rock that are sliding in translation, right, on a defined failure surface. This is very similar to rock block sides, right? But generally, rock block sides are just bigger cousins of your rock slides. And in other classifications, they are essentially belong to one class. And then you also have your rock avalanches. And avalanches, the important feature in them is that these are really high velocity failures, and they can initiate from a rock fall, a rock slide, or anything. But the distinguishing characteristic of an avalanche is it has to start from a great height, like a minimum 150 meters relief, and as it goes down, the material disintegrates, and it can exert a lot of air pressure in its surroundings. It can create an air blast. And then finally, you have your rock slumps, which are actually more closer to soil slumps than rock failures. I mean, rock slumps mostly involve weak rocks like shales or highly weathered rocks. All right. And when you're talking about when in an engineering sense, rock slumps and soil slumps are more or less the same. Okay. I think their division is mostly an artificial geological division. But if you're talking about the engineering side, they behave the same. They fail under a rotational failure plane. So they have a circular failure plane, right? And yeah, they can fail at minimum slope angles of 15 degrees. So that's quite gentle. Okay. So it's difficult to appreciate all those fucking words. So I compiled some videos showing how they work in real life. So this is a rockfall, and you can see here a big block detaching and falling and rolling down. Okay. It's pretty nice to see them in action. I mean, this is my recent realization. It's difficult to teach mass movement without showing people how they work in real life. All right, this is a rock slide or a block slide. It's this image is a dead giveaway. I mean, you can see the surfaces are more or less really planar. I mean, if you have a good eye in geology, you can see here that the bedding planes here are quite obvious. Okay, you can see here really obvious bedding planes that are just projecting out of the road cut. And note how the movement or even the initial movements are just following the bedding planes, right? So this is a classic rock slide or rock block slide. And yeah, it's almost purely translational in terms of movement. So I had a difficult time looking for a good video of a rock avalanche. Oh damn. So this is supposedly a video. I'm not sure. I can't seem to be able to interact with the video. I mean that's a shame. But more or less you can see here you can see in this GIF that you have a relatively really high relief here, and the failure here probably started as a rock fall, okay, but it simply disintegrated, and its collapse resulted in a massive blasting of the water beneath. Okay, and then the other GIF in here is a simulation of a rock avalanche. Okay, so you can see more or less how it started as a relatively small failure, and then branching out and then traveling quite a long distance as it failed. Okay, so that's another characteristic of an avalanche. It can travel really long distances. So that's the video. Good.
Ora.
right? So at least you're able to appreciate the sheer scale of the rock. And this is an example of a rock or soil slump. So remember, in a rock or soil slump or in a rotational slide, the key feature here is a rotational failure surface. And this is mainly driven by the inherent weakness of the whole slope material itself, right? So when your whole slope material is equally weak in all directions, the tendency of the failure is to just look for the most unstable uh, plane in which it can fail. So you more or less have an equal chance of failing at any of these planes, but eventually the slope will just find the most efficient way to fail. This is in contrast with a rock slide, a transition slide where you have more or less a defined failure surface, and the failure simply exploits that failure surface. In the case of a slump or a rotational slide, the driving forces create or define where the failure surface will occur. So this is a drone shot of a massive rotational slide. This failure is basically we have a headscarf that underwent displacement. So this part went down. Alright, and you have a scarp in here. And then this part is actually bulging. And as you can see in the video, there was a road that was displaced. Right, so that's the road that was displaced by the slide. All right, now let's talk about the soil slopes. And there's a lot here. So you have soil falls, soil avalanches, disrupted soil slides, soil slumps, soil block slides, soil earth flows, flow slides, subaqueous flows, and lateral spreading. Now note that soil falls are typically just your boulders that are bound in a clay material. So typically this could be weathered basalt or weathered andesites, right? Or weathered volcanic rocks that contain core stones. So you have core stones which are relatively fresh and solid, and they're encased in a clay soil. So as they weather out, they can detach from their clay binder and fall as a boulder fall. Okay, this is quite common, I think, in Zambales, Bataan area. Soil avalanches, they're essentially just avalanches. I mean, it's difficult to distinguish soil avalanche, debris avalanche from rock avalanche. They are a spectrum. Okay, it's quite impractical to differentiate those three avalanches. Disrupted soil slides. I think these are dry slopes of sand that fail during an earthquake, and they just flow out. Okay? They flow out like a sand in an hourglass because they are so dry, they easily flow out. And then you have soil slumps, which are, yeah, just same as the rock slumps. And then you also have your soil block slides. These are just normally just really thick layers of soil that are more or less compacted or consolidated, and they simply separate from another layer. Or earth flows are quite interesting. They are driven by the plasticity of your soil. So earth flows are slow moving failures, and typically it's a mixture of clay and silt and other fine soils. And what happens here is when you have clays or silts that are able to take up a lot of water, okay, like clays and silts that have a high plasticity index, okay, when they have a high plasticity index, they are able to tolerate a lot of water before they turn into fluid. So these things can take up a lot of water and they become very, very soft and very plastic. And they can eventually just flow out. Okay, they just deform very, very slowly. And then you also have flow slides, which are just a manifestation of liquefaction. Okay, flow slides are just liquefaction in embankments like dams or road embankments. But these are most common in dams, the flow slides. Subaqueous flows, I think this is happening in the coasts, but it's difficult to find examples of these ones. Lateral spreading, we've discussed that earlier. All right, so this is an example of a soil fall. So you can see here the boulder, and you can basically have here outcrops, relatively weathered outcrops that probably contain mixtures of boulder and soil. This is a video of an earth flow. This is really interesting because in my profession, I see a lot of misinterpretation of what an earth flow is. People confuse earth flow with debris flow, which is wrong. Earth flow and debris flows are completely different animals. earth flow is driven by the plasticity of your soil, while debris flow is driven by by the excess water. Right? So you can see here, it's really moving really slowly, and this one is deforming plastically, right? It's not technically flowing; it's just deforming continuously. So the main constituents in earth flows are clays and silts. And normally your soils here are not yet fully saturated. Okay? They are still within their plastic limits. Okay, so they're not fully saturated. So they're still partly dry. Right? So earth flows are actually more common than you might actually think. This video is just a classic video of how an earth flow will move if it's moving relatively in a relatively faster velocity. But in my experience, I've seen a lot of these in the Philippines, although they move much slower, like a few meters in a year, right? So yeah, as I've mentioned, earth flow is all about clays and silts that are not fully saturated, but have enough water to make them deform plastically. Okay, so they undergo permanent deformation, but they're not really flowing. They're just moving. They're just creeping. They're just deforming continuously. Right now, flow slides, as I mentioned before, are just dams. They're most commonly flow slides are just liquefactions in embankment dams. So flow sides also involve debris flows, right? Normally because flow sides involve highly saturated materials that fail. Of course, as they fail, you have a highly saturated material. If it lands on a steep or a channeled area, it can transform into a debris flow. All right, and remember that debris flow is driven by excess water. Okay, so at this point, debris flow is more of a water with soil. Okay, water that is carrying some soil. In the case of earth flow is still more about soil that happened to be wet. Right, so you can see here that the materials is really flowing. It's very fluid. right? So debris flows are mostly driven by the fluids. All right, now there are two main categories on how we evaluate the stability of a slope in terms of seismically driven instabilities. First is to treat them as more as a static slope. So it's an inertial slope stability analysis. So what happens here is we treat the process as a static process. Okay, so we simplify the dynamic earthquake stresses as a static load or a dead load. Okay, so we try to convert that shaking into a equivalent dead load. Okay, and this simplification is mostly applicable to materials that are able to retain their shear strength during an earthquake. So what are the materials that can do that? So materials that do not liquefy or and do not undergo strain softening and are not brittle. So it's quite hard to define what is a material that is able to retain its shear strength during an earthquake because a lot of materials lose strength during an earthquake. So non-liquefiable soils, what are the non-liquefiable soils? So basically the soils that are dry and are so soils slope should be dry or and typically could be okay, it should be dry. Non-strain softening, soils that are strain softening mostly are your clays. Okay, sorry, it should be not clay. As we will be discussing later on, all right, clays have a special property, or to be specific, clay minerals in soil. If you look at them under the microscope, all right, clay minerals are actually like plates. So if you look at the clays under the microscope, they are like plates that are arranged in random or in random patterns. Okay, so this random pattern actually uh, provides some form of interlocking between your clay grains, and they provide some form of frictional resistance. Now, what happens when you have an earthquake is that the clays are more or less they are rubbed together. They are more or less ru- uh, consistently being rubbed or sheared together, and the effect of shearing or constant rubbing or constant shaking due to earthquake is that the clay minerals can end up aligning to the direction of the shear stress. So they can align parallel, and the effect here is that they lose their frictional resistance. They lose their interlocking, and they become weaker. Okay, so that's basically how strain softening works in clay soils. Non-brittle. So typically non-brittle materials are your typically non-brittle materials are your ductile materials. So cannot be rocks. Okay, rocks are brittle. Okay, so materials that can retain their shear strength during an earthquake should be dry, should not be clay, and should not be a rock. So typically these can include dry sands, all right, dry sands to silts, gravels, and some really uh yeah, mostly those types of soils, all right. Now for weakening slope stability analysis, this is an analysis that will actually account for the reduction in shear strength during the earthquake, and we will be just discussing that later on. All right, so for the next topic, let's discuss the tsunami and seiches. So tsunami are essentially just giant waves, and the key word in tsunami is that they are generated by vertical displacement of water. Okay, keyword is vertical displacement. Shaking does not produce tsunami. Vertical displacement does. So if you have a strike slip fault earthquake that is purely lateral, you won't get a tsunami. Right? So typically the most common areas that generate tsunamis are your subduction zones which involve really large areas. So earthquakes in subduction zones involve large areas of faulting, and you also have a lot of vertical component in subduction zones. So they are the prime spots where you can generate a tsunami. And another feature of a tsunami is that it's damn freaking huge, right? It has a wavelength of in the order of kilometers. So the wave is so the a tsunami wave in the ocean in the deep ocean basically can have a length of in the order of a kilometer. Okay? And big waves, all right, they can travel really fast, and they just ignore obstacle. They more or less can ignore, lose very little energy. Okay, because they don't have to oscillate a lot in order to travel long distances. I mean, one one wave period is already one equivalent to 1 kilometer. Okay, so tsunamis from the Pacific or from the middle of the ocean can easily hit really far away areas. Okay, it's not uncommon to have a tsunami generated somewhere in the middle of the Pacific to affect Chile, Japan, and other Pacific areas. Okay, and what happens in tsunami is that when they approach the coasts or the shore, all right, they sort of shorten. Okay, so they start off as a long wavelength wave. As they approach the shore, they just sort of They compress. They compress horizontally, and they increase in height. So they're squeezed, and they reach really high heights. All right, and they can attain a run-up height. So a run-up is defined as the maximum vertical height onshore above sea level. So how high the tsunami can rise above the sea level, all right? So that's the run up height. And tsunamis can easily reach between 10 to 30 meters and probably even higher. Sizes are they're similar to water sloshing back and forth in a pool or bathtub or a cup of water. As you can see here in this video, this is a swimming pool, that was affected by an earthquake, and you can see the waves here are just they're just going back and forth. All right, and what generates seishes is that when you have big earthquakes, all right, big earthquakes involve big movements, and big movements involve long period seismic waves. And just like tsunami, and long period seismic waves can also travel really long distances. All right, so size seiches can be generated by distant earthquakes as long as that earthquake is large. So what happens here is that these long period earthquakes induce large waves within the body of water, and the confined nature of that body of water actually just forces the wave to just bounce around the body of water continuously until it expends all its energy, rebounding and rebounding. Right. So thanks for listening. This lecture is mostly based on the textbook of Day 2012 titled Geotechnical Earthquake Engineering Handbook.